Okay, I'm going to look at two problems from chapter 2. These are not suggested problems, but they are interesting and they're worded a little bit differently, so it might help you with your thinking process, some mapping. So these are problems 91 and 93. So problem 91 it's not a mechanics problem actually. A fast food restaurant uses a conveyor belt to send the burgers through a grilling machine. If the grilling machine is 1.1 meters long and the burgers require 2.5 minutes to cook, how fast must the conveyor belt travel? If the burgers are spaced 15 centimeters apart, what's the rate of burger production in burgers per minute? Okay, so when you read this, it's just, looks very, very strange, but I think it would really help to draw some figures. So this is my conveyor belt. It's 1.1 meters long. You put the burgers here and then they travel. Okay? And presumably you put a lot of burgers on it. They're just spaced 15 centimeters apart, so much, much denser than this one. That you put more, if you fit more burgers on this conveyor belt. They're asking, the burgers require 2.5 minutes to cook. So presumably they're cooked while they're on the conveyor belt, so they cook during their travel from here to here. So the time it takes must be 2.5 minutes, which is what, 120 plus 30, 150 seconds. Okay? So they travel over 1.1 meters in 150 seconds. What will be the speed of the conveyor belt, which would of course be the speed of the burgers? Well, speed is delta x by delta t. You take the ratio of these two numbers, whatever comes out. Okay? And then they're asking, if the burgers are spaced 15 centimeters apart, this is 15 centimeters, what's the production rate in burgers per minute? Burgers per minute. Now, how would you approach this? How many burgers would actually, would be leaving the conveyor belt on the average? Now, of course, sometimes a burger is just going to leave at the very beginning of your minute, and sometimes they're going to, they had just left, so burger is just going to wait for, travel for another 15 centimeters and then leave the conveyor belt. But we're looking for the average value, so we're just going to assume the burgers are kind of spread. And on the average, over 15 centimeters, there's just one burger. Okay? This is the way I would approach this problem. You can approach this, of course, other ways as well. But how would you do this? How would you calculate the burgers per minute? At every 15 centimeters, there's going to be a single burger. Okay? So at 1.1 meters, there's going to be a certain number of burgers, right? Over the belt. There are, 1.1 divided by 0.15 burgers. This is an average number. This is the average number of burgers on the belt. And of course, sometimes there's going to be more, sometimes there's going to be less. One more, one less. So this is, when you round this up, you're going to get an integer. It's going to be plus or minus 1 with respect to that integer. Okay. But this is the number of burgers on the belt. And the belt gets completely emptied over 2.5 minutes. So this divided by 150 seconds is going to be my burger production rate. I have this many burgers on the belt, and I clear the belt in 150 seconds, so I must be clearing this many burgers per this many seconds. That's my production rate for this fast food restaurant. Okay. So this is, like, as I said, is not a suggested problem, and it is something with the ratios and so on and so forth. Try to understand this. And if it's clear to you, then fine, just skip this problem. This is not something hard or tricky or particularly useful, but understanding ratios and how to approach them outside the context of mechanics is important. Now, the second problem I want to look at is problem 93. And here it is a mechanics problem. We are given a graph of two bicycles. Their position is a function of time. And one of them starts at origin, moves on a straight line. This is our bicycle B. And the other one starts, somewhat ahead, and then goes like this. This is our bicycle A. This is like a parabola in the figure, okay? And it doesn't necessarily start at zero slope, maybe a little bit of a slope, okay? If you look at the figure more carefully. Now they're asking a number of questions. Is there any instant at which the two bicycles have the same velocity? Yes, there is. Okay? This bicycle is starting from behind, it's taking over, it's starting with a lesser velocity, it's ending up with a higher velocity. At some point, by the mean value theorem, it has to actually have the same velocity as this one. This is constant velocity motion. Bicycle B does constant velocity motion. Bicycle A, if this is a parabola, does constant acceleration motion. That point will be here. Okay. Slopes, which is same as velocities, equal. Okay. So you will draw the slope, it increases, here it's equal and then it gets larger. At that point, the velocities are equal. Their positions are not. Okay. This is still behind, there's still a positional difference between them, but their velocities are going to be equal. Which bicycle has the larger acceleration? Bicycle B has no acceleration, bicycle A has some acceleration, so it has the larger acceleration. At which instance are the bicycles passing each other? So here, at this instant, bicycle B is passing bicycle A. Before this, its position is less than bicycle A. After this, it's more, so they're just taking over. At this position, they're the same. Here, B is taking over A. Here, A is taking over B. Just before this point, A's position is less than B. After that point, A's position is more than B, so it's overtaking B at that point. Which bicycle is passing the other? I already said that. Which bicycle has the highest instantaneous velocity? Now, this is constantly increasing its velocity. After this point, at every point, its instantaneous velocity is larger than B. Which bicycle has the higher average velocity? Now, that one, let's see if I have another color chalk here. It's very hard to tell this quantitatively, but how would you calculate the average velocity of this one? Well, you would look at, delta x b and delta tb. It would actually be the slope, over here. Now, for the other one, for the other bicycle A, your delta x is going to be from here to here. This is delta XA, and your time is going to be from here to here, delta T A, and I'm going to complete this to a straight line. It will be the slope of that line. Now, my drawing is not very accurate, but neither is the drawing on the book. I would say that they look approximately the same. Okay? So the slope of this line that's connecting these two endpoints, and the slope of this line that's connecting these two endpoints, which is actually the line in this graph, they seem to have the same slope. Okay? Since they have the same slope, these two lines, then I would say they have the same average velocity. The slope corresponds to the average velocity, obviously, and it's very hard to tell either from my drawing or from the book. I suspect they are approximately the same. Yeah, and that's it.